This is SpaceTime Series 27, Episode 30, for broadcast on the 8th of March 2024. Coming up on SpaceTime, could a hypothetical Axion star pinpoint where and what dark matter is? A new study looking at Martian groundwater? And we pose the question, is it possible to fry food in space? All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers plan on using the expected characteristics of a hypothetical type of star to improve their understanding of mysterious dark matter. The star is known as an Axion star. It's never been seen, and even its component axions are just hypothetical. First theorized back in 1977, axions, if they exist, are light mass particles that could be a contender for dark matter due to the heat they should be giving off. However, due to the wide range of sizes and masses that they could possibly be, their potential discovery has remained elusive. Now, a series of papers reported in the journal Physical Review Letters suggest that a new approach to locate this wonder particle, if it exists, could explain both dark energy and dark matter. One of the study's authors, Malcolm Fairbairn from King's College London, says axions are one of the prime candidates for dark matter. Fairbairn and colleagues theorized that they would have the capacity to heat the universe just like supernovae in ordinary stars after coming together in dense clumps. And it's those dense clumps that provide a target to search for. Einstein's general theory of relativity suggests that around 85% of the material of the universe is dark matter, a mysterious invisible substance which scientists know exists because they can see its gravitational impact on ordinary baryonic matter, the stuff stars, planets, cars, people, dogs and cats are made out of. Observations show that some invisible matter, is preventing galaxies from spinning apart as they rotate, and that invisible matter has been named dark matter. But scientists have no idea what dark matter is, and the hypothetical Axion particle is one of the contenders. Axions would be extremely low-mass particles, but they must be present in very large numbers to explain the amount of dark matter which we infer from galaxies. Now, according to this new hypothesis, they could also be packed very densely into specific areas, meaning they're subject to the laws of quantum mechanics, and that would mean individual axions would begin to act in concert. And that suggests there could be large groupings of axion, possibly as dark matter, at the center of galaxies. And these could be the so-called Axion stars that the authors are talking about. But these Axion stars would become unstable once they move beyond a certain mass threshold, exploding into the electromagnetic spectrum through radiation and photons. The authors suggest that these explosions have the potential to have heated the intergalactic gas that existed between galaxies in the time between the Big Bang 13.82 billion years ago and the formation of the first stars some 50 to 500 million years after the beginning of the universe, a period we refer to as the Cosmic Dark Ages. Now, all this would change the way the cosmic microwave background radiation will look during this period of time. The cosmic microwave background radiation is the leftover heat from the Big Bang, now cooled down to just 2.7 degrees above absolute zero. Scientists can observe this cosmic microwave background radiation through the hydrogen 21 centimeter measurement. So, by looking for signals of where Axion stars might have exploded in the early or present universe, scientists may be able to use these methods to track down the so far unobserved Axion and discover the sources of some, if not all, dark matter. Fairbairn says coherent Axion stars, even those which are relatively compact, have the potential to burst into a halo of electromagnetism and light. Knowing the kind of structures Axion dark matter can form and its impact on the surrounding intergalactic gas could pave new ways for its detection. Being able to find axions would therefore help scientists and physicists solve one of science's big questions over a century in the making, and at the same time help lay bare the history of the early universe. By computing the total number of Axion stars in the universe, and by extension their latent explosive potential and intergalactic gas, the authors have also surmised the size of the signal that Axion stars would give out in the cosmic microwave background radiation. And this would allow the 21cm measurements to categorize what is and what isn't originating from axions accurately, thereby aiding in the search. This is SpaceTime. Still to come, we look at the story of Martian groundwater. And we ask the question, would it be possible to fry foods in space? All that and more still to come on SpaceTime. Scientists studying the red planet Mars have begun searching for possible underground water supplies. But a new study predicts there'd be very little groundwater recharge in the ancient Martian aquifers. There's plenty of evidence that Mars was once a warm, wet world. The geological record of the red planet shows evidence for water flooding across its surface, forming river deltas and valleys carved out by massive flash floods. In fact, much of the Martian northern hemisphere may once have been a giant red planet ocean. But a new study reported in the journal Icarus shows that no matter how much rainfall fell on the surface of ancient Mars, it seems very little of it seeped into an aquifer on the planet's southern highlands. Scientists made the discovery by modelling groundwater recharge dynamics for the aquifer using a range of methods from computer models to simple back-of-the-envelope calculations. But it turns out that no matter the degree of complexity, the results converged on the same answer, a minuscule 0.03 millimetres of groundwater recharge per year on average. That means that whatever rain fell in the model, only an average of 0.03 millimetres per year could have entered the aquifer and still produced the landforms remaining on the planet today. Now, for a comparison, the annual rate of groundwater recharge for the Trinity and Edwards Trinity Plateau aquifers, which provide water to San Antonio in Texas, generally ranges from 2.5 to 50 millimetres per year, or about 80 to 1,600 times more than the Martian aquifer recharge rate. The study's lead author, Eric Hyatt from the University of Texas at Austin, says there's a variety of potential reasons for such a low groundwater flow rate. When it rains, the water may mostly have washed across the Martian landscape as runoff, or it may just not have rained very much on Mars at all. These findings can help scientists constrain the climatic conditions capable of producing rainfall on early Mars. They also suggest a very different water regime on the red planet compared to what exists on planet Earth today. Hyatt says the fact that the groundwater isn't as big of a process on Mars could mean that it just didn't rain very much on the red planet, or that runoff might simply be more important. What it does show is just how fundamentally different the two planets Earth and Mars really are. The models used in the study work by simulating groundwater flow in a steady-state environment where inflow and outflow of water into the aquifer is balanced. The study also incorporated modern topographical data collected by satellites. Hyatt says Mars still preserves one of the planet's oldest and most influential topographical features, an extreme difference in elevation between the northern hemisphere lowlands and the southern hemisphere highlands, known as the Great Martian Dichotomy. And this dichotomy preserves signs of past groundwater upwelling, in which groundwater rose up from the aquifer to the surface. The authors used geological markers of these past upwelling events to evaluate different model outputs. Understanding groundwater flow can help inform scientists of where to find water on Mars today. Whether you're looking for signs of ancient Martian life, or simply trying to sustain human explorers on the red planet, or making rocket fuel to get back home to Earth, it's essential to know where the Martian water is most likely to be. This is SpaceTime. Still to come, is frying food possible in space? And the March equinox, the constellations Taurus, Leo, Corvus and Eridanus, and don't forget Pi Day, are among the highlights of the night skies on March Skywatch. Well, if you like your fries and hash browns as much as I do, then there's one very obvious question that you ask yourself when it comes to space travel. Is it possible to fry foods in microgravity? And it's a legitimate question. You see, the food we eat determines how we feel, and as far as I'm concerned, nothing beats a good old fry-up, although in moderation, of course. As we prepare for missions to the Moon and eventually onto Mars and beyond, astronauts will be happy to hear that one single comfort food is no longer out of reach, even in space, and that food is fries. Even though frying potatoes is done everywhere around the world, it involves complex physics and chemistry, and of course in space everything becomes more complicated. You see, without gravity and therefore the buoyancy pulling upwards, bubbles might stick to the surface of the potato, shielding the potato in a layer of steam that might leave it undercooked. To study how microgravity influences cooking techniques such as frying, a novel experimental carousel-type apparatus was designed to be safe while also operating in microgravity conditions on a parabolic flight aboard a Vomit Comet airliner. The experiment filmed the frying process with a high-speed, high-resolution camera in order to capture the bubbling dynamics, such as growth rate, size and distribution. As well as the escape velocity from the potato, the bubble's speed and direction of travel in the oil was also noted. The experiment also measured the temperature of the boiling oil, as well as the temperature inside the potato. Scientists reporting in the Food Research International Journal found that shortly after the potato was added to the oil in low-gravity conditions, vapor bubbles detached easily from the potato surface, just like they do here on Earth. And that's gotta be a good news story. This is SpaceTime. And time now to turn our eyes to the skies and check out the celestial sphere for March on Skywatch. Happy New Year! Well, it would be if this was ancient Mesopotamia or Rome. That's because March was the first month of the new year, going back to the earliest concept of celebrating New Year's Day at the time of the Vernal Equinox, around 2000 BCE. See, the ancient Roman calendar, which had just 10 months, designated March 1st as the new year. That 10-month calendar is still reflected today, with the name September or Septem being Latin for 7, October or Octo meaning 8, November or Novem 9, and December or Deci meaning 10. It wasn't really until the Gregorian calendar that January 1st marked the start of the new year. But in the beginning it was mostly Catholic countries that adopted it. Protestant nations only gradually moved across, with the British, for example, not adopting the reformed calendar until 1752. Prior to that date, the British Empire and its American colonies still celebrated New Year's Day on March 25th. The highlight of the month is the March equinox, which this year takes place at 14:06 in the afternoon of Wednesday, March the 20th, Australian Eastern Daylight Time. That's 23:06 in the evening of Tuesday, March the 19th, US Eastern Daylight Time, and 3:06 in the morning, Greenwich Mean Time. For our listeners in the Northern Hemisphere, it means the vernal equinox, the start of spring, while those south of the equator, it's the autumnal equinox, meaning a move into autumn. The day marks the point in Earth's orbit around the Sun, when the planet's rotational axis means the Sun will appear to rise exactly due east and set exactly due west to someone standing on the equator. It means almost equal hours of darkness and light. In fact, the very word equinox is derived from the Latin, meaning equus or equal, and nox meaning night. It all comes about because Earth's rotational axis is tilted at an angle of around 23.4 degrees in relation to the ecliptic, the plane created by Earth's orbit around the Sun. That axial tilt is always pointed at the same position in the sky, regardless of Earth's orbital position around the Sun. So, on any other day of the year, either the northern or southern hemisphere is tilted more towards the Sun. But on the two equinoxes, usually around March 21st and September 23rd each year, the tilt of Earth's axis is directly perpendicular to the Sun's rays. However, there's a complication called precession. This causes Earth's spin axis to wobble ever so slightly, just like the axle of a spinning top. The rate of precession is only about half a degree per century, so people don't notice it on human timescales. And because the direction of Earth's axis of rotation determines at which point in Earth's orbit the seasons occur, precession will cause a particular season, for example the Southern Hemisphere autumn, to occur at a slightly different place from year to year over a 21,000-year cycle. At the same time, Earth's orbit itself is subjected to small changes called perturbations. See, Earth's orbit's an ellipse, and there's a slow change in its orientation which gradually shifts the point of perihelion, Earth's closest orbital position to the Sun. Now, these two effects, the precession of the axis of rotation and the change in the orbit's orientation, work together to shift the seasons with respect to perihelion. And because we use a calendar year that's aligned to the occurrence of the seasons, the date of perihelion gradually regresses through a 21,000-year cycle. And there's another complication. Australia and some of the other Commonwealth countries start their seasons on the first day of the month, what are referred to as meteorological seasons, rather than on the solstices and equinoxes, which are referred to as astronomical seasons. So that means Australia's autumn officially began on March 1st rather than on the day of the March equinox. Meteorological seasons are used because it makes it easier for meteorologists and climatologists to break the seasons down into more exact 3-month calendar groupings for comparing seasonal and monthly statistics. The moment of the March equinox is also important in astronomy because it's used to define the celestial coordinate system of right ascension and declination. In astronomy, the celestial coordinate system is the astronomical equivalent to the latitude and longitudinal coordinates used on Earth's surface. It's used to specify the position of objects in three-dimensional space and the direction of those objects on the celestial sphere, the imaginary globe surrounding the Earth. In other words, it lets scientists determine the position of a celestial object, such as a satellite, a planet, stars, galaxies, and so on. Right ascension, which uses the symbol alpha, is the angular distance measured eastwards along the celestial equator from the vernal equinox. On the celestial sphere, it's analogous to terrestrial longitude. Declination, which uses the symbol delta, measures the angle north or south of the celestial equator, and so it's the celestial equivalent to terrestrial latitude. Marking the vernal equinox and setting the western evening sky this time of year is one of the oldest recognized constellations in the heavens, Taurus the Bull, so named around 6,000 years ago. In Greek mythology, Taurus represents the king of the gods, Zeus. Zeus lusted after King Agenor's daughter Europa, who was looking after a herd of cattle. Now, being a god and with godlike powers, Zeus decided to transform himself into a powerful white bull so that he could get closer to the beautiful Europa. Now, once transformed into a bull, Zeus convinced Europa to climb on his back, and he then carried her off to the island of Crete. Taurus's head is represented by a dominant V-shaped grouping of stars. The bright reddish star in the group is Aldebaran, an orange giant 1.5 times the mass of the Sun, located 65 light-years away. A light-year is about 10 trillion kilometres. The distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Aldebaran is the 14th brightest star in the night sky and the closest bright star to the point of the vernal equinox. In ancient Arabic, Aldebaran's name means the follower, as it appears to follow the 7 sisters of the Pleiades. It's also the first of the 4 royal or guardian stars identified by the ancient Mesopotamians. Now, that V-shaped grouping of stars near Aldebaran is known as the Hyades. It's the nearest young open star cluster to Earth, located just 153 light-years away. Between Aldebaran and the Orion constellation, you'll see a bright red star. That's Betelgeuse, the 9th brightest star in the night sky, these days more commonly called Betelgeuse. If you turn to the north now, you'll see the 2 bright stars Pollux and Castor, which represent the northern constellation of Gemini the Twins. In Greek mythology, they were brothers who travelled with Jason aboard the ship Argo in search of the Golden Fleece. Pollux is an orange-hued evolved giant star, located 34 light-years away. It has about twice the Sun's mass and is bloated out to around 11 times the Sun's diameter. In 2006, an extrasolar planet or exoplanet, designated Pollux b, was discovered orbiting the star. The planet is a gas giant, orbiting its host star every 1.61 Earth years. The other star, Castor, is located some 51 light-years away, and it's actually a system of 6 stars comprising 3 eclipsing binaries. Eclipsing binaries are binary star systems in which the orbital plane of the two stars in the system lies so nearly along the line of sight from the observer here on Earth that the stars appear to eclipse each other. Looking to the northeast now, and you'll see the star Regulus, or Little King, the brightest star in the constellation Leo the Lion. Leo is mentioned by Homer in his famous 8th century BCE poem, the Odyssey. According to Greek mythology, Leo was killed by Hercules as the first of his 12 labours. Located some 79 light-years away, Regulus is a multiple star system composed of at least 4 stars. Regulus A, designated Alpha Leonus, is a spectroscopic binary comprising a rapidly spinning spectral type B blue-white star, around 3.5 times more massive than the Sun, with some 288 times the Sun's luminosity, and a small companion star, most likely a white dwarf, the stellar corpse of what once would have been a Sun-like star. The pair take about 40 days to orbit each other. Spectroscopic binaries are double star systems orbiting each other so closely and at such an angle that they can only be visually separated, from our viewpoint here on Earth at least, by their spectroscopic signatures. Astronomers describe stars in terms of spectral types. It's a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, then spectral type G yellow stars. That's where our Sun fits in. Then there's spectral type K orange stars, and the coolest and least massive of all stars are spectral type M red stars, commonly referred to as red dwarfs. Each spectral classification system is further subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest. And then you add a Roman numeral to represent luminosity. So, our Sun technically is a G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were born as spectral type M red dwarf stars but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a unique category between the largest planets, which can have around 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are around 75 to 80 times the mass of Jupiter, or about 0.08 solar masses. The primary star in Alpha Leonis completes a full rotation around its axis in under 16 hours. That's incredibly quick, especially when compared to our Sun's 30-day rotational period. Now this gives the primary star an oblate appearance, and it causes what's known as gravity darkening, meaning its poles are considerably hotter and 5 times brighter per unit surface area than its equatorial region. Scientists estimate that if it were rotating just 15% faster, the star's gravity would be insufficient to hold it together, and it would literally spin itself apart. Located further away are Regulus B, C and D, which are all dim main sequence stars. Main sequence stars are those undergoing hydrogen fusion into helium in their core, like the Sun's currently doing. Regulus B and C are thought to orbit each other every 600 Earth years and are located around 5,000 astronomical units away from Regulus A. An astronomical unit is the average distance between the Earth and the Sun, around 150 million kilometres or 8.3 light minutes. Regulus B is a spectral type F white-yellow star, while its companion Regulus C is a small spectral type M red dwarf star. Regulus D is a bit more of a question mark. It's a dim star, and, at least from our point of view, it appears to be sharing motion across the sky with other members in the group. At the opposite end of the constellation of Regulus is the star Beta Leonis, or Denebula, the horse's tail. It's a luminous white star thought to be spectral type A, about half as bright as Regulus, and the third brightest star in the constellation Leo. Beta Leonis has about 1.8 times the mass of the Sun and about 15 times the Sun's luminosity. It's suspected of being a dwarf Cepheid or Eta Scuti type variable star, meaning its luminosity varies very slightly over a period of several hours due to pulsations on its surface. Also at the other end of Leo are the stars Theta and Iota Leonis, the loins of the lion. Theta Leonis is about 165 light-years away. It's a very young spectral type A white star, about 2.5 times the mass of the Sun. With an age of just 550 million years, Theta Leonis' spectra shows enhanced absorption lines for metals, that is, elements other than hydrogen and helium. This increased metallicity appears around 12% higher than the Sun, allowing the star to radiate with some 141 times the luminosity of the Sun from its outer atmosphere, at an effective temperature of 9,350 Kelvin, literally giving it a white-hot glow. Located some 79 light-years away, Lota Leonus is another spectroscopic binary, consisting of two stars orbiting each other every 183 Earth years. The primary star is a spectral type F yellow dwarf star, a little hotter and more massive than the Sun. Algebra, or Gamma Leonis, is a binary star system with a visible third component. The two primary stars are located 126 light-years away and can be resolved in a backyard telescope. Both are yellow giants, orbiting each other every 600 Earth days. The unrelated tertiary star, named 40 Leonis, is a yellow tin star which can be seen through binoculars. Its traditional name, Algebra, means the forehead. Other stars in the system include Delta Leonis or Zosma, which is a blue-white star 58 light-years from Earth, Epsilon Leonis, a yellow giant some 251 light-years from Earth, and Zeta Leonis, an optical triple star. The brightest component is a white giant about 260 light-years from Earth, while the second brightest star, 39 Leonis, is widely spaced and is located to the south of the primary, with the third and faintest star in the system, 35 Leonis, located to the north. Also located in Leo is Tau Leonis, visible as a double star through binoculars. It includes a yellow giant located some 621 light-years from Earth, and a binary secondary star 54 Leonis, a pair of blue-white stars divisible in small telescopes and located 289 light-years from Earth. Also in the constellation Leo, you'll find the Leo Triplet, a group of three galaxies, Messier 65, Messier 66, and NGC 3628, all appearing relatively close together. Messier 65, also known as NGC 3623, is an intermediate spiral, possibly barred spiral galaxy, about 37 million light-years away. M65 disk appears to be slightly warped, and a relatively recent burst of star formation is suggestive of some gravitational interaction with the other two galaxies in the Leo Triplet, possibly around 800 million years ago. Nearby is Messier 66, or NGC 3627, another intermediate spiral galaxy, some 95,000 light-years wide and about 36 million light-years away. Gravitational interaction from its past encounters with the neighbouring galaxies in the triplet has resulted in an extremely high central mass concentration, a high molecular to atomic mass ratio, and a resolved non-rotating clump of neutral atomic hydrogen apparently removed from one of its spiral arms. The third member in the group is NGC 3628, the Hamburger Galaxy, a spiral galaxy with a spectacular 300,000 light-year long tidal trail of gas and stars. NGC 3628 is located 35 million light-years away. Its most conspicuous feature is the broad and obscuring band of dust located along the outer edge of its spiral arms, effectively transecting the galaxy to the view from Earth. Other bright well-known galaxies in Leo include Messier 95, Messier 96, Messier 105, and NGC 2903. M95 and M96 are both spiral galaxies, each about 20 million light-years from Earth. M95 is a barred spiral. Another barred spiral galaxy is NGC 2903, which is thought to be very similar in size and structure to our own Milky Way galaxy. It was discovered by William Herschel in 1784. Close to the M95-M96 pair is the elliptical galaxy M105, which is also around 20 million light-years from Earth. Okay, let's turn to the east now and the constellation of Corvus the Crow. In Greek mythology, Corvus was a really clever crow. In fact, he could talk to people. However, after refusing to speak to the god Apollo, he was banished to the sky, together with Crater the Cup and Hydra the Snake. One of the brightest stars in Hydra is Alphard, the solitary one, so named because it appears all alone in the sky. Okay, turning to the western horizon now, and you'll see the star Achernar in the southern tip of the constellation Eridanus the River. Eridanus is one of the largest and longest constellations in the sky. Achernar means the river's end, as it marks the end of the river Eridanus. Located around 139 light-years away, Achernar is a binary star system comprising two stars, Alpha Eridani A and Alpha Eridani B. one of the 10 apparent brightest stars in the night sky. Alpha Eridani A is a young, hot spectral type B blue star, about 6.7 times the mass of the Sun, with a stunning 3,150 times the Sun's luminosity. Acherna's extremely high rotational velocity of over 16 kilometers per second gives it an oblate shape, making it one of the least spherical stars in the Milky Way, with an equatorial diameter some 56% greater than its polar diameter. This distorted shape means the star displays significant latitudinal temperature variations, with its polar temperature being above 20,000 Kelvin, while its equatorial temperature, being much further away from the stellar core, is only around 10,000 Kelvin. Those high polar temperatures are generating a fast polar wind, ejecting matter from the star and generating a polar envelope of hot gas and plasma. The companion star, Alpha Eridani b, appears to be a spectral type A white star with about twice the mass of the Sun. The two stars orbit each other at an average distance of roughly 12.3 astronomical units. Now, just a quick reminder that March 14th marks the yearly celebration of the mathematical constant pi. Pi is the ratio of a circle's circumference to its diameter. But it's also an irrational number, meaning its decimal representation never ends and never repeats. More than just a number, pi has important applications in astrophysics, orbital mechanics, and other fields of astronomy. It's been calculated to over 1 trillion digits, and the current record for reciting pi from memory is over 70,000 digits. Imagine sitting next to that person at a dinner party. As for me, 3.14159 is about it. Of course, as well as Pi Day, March 14 is also the birthday of the great Professor Dr. Albert Einstein. Science writer Jonathan Nally from Sky and Telescope magazine joins us now for the rest of our tour of the March night skies.
G'day, Stuart. Well, we'll start with the view to the south, which we normally do, which is where we find plenty of bright stars and constellations to see this time of the year. First of all, of course, there's the Southern Cross, which is quite easy to see at the moment. It is lying on its left-hand side, so you've got to bear that in mind when you go out to have a look at it. It's not standing upright. It's on its left-hand side. And by cross, we mean it's a crucifix shape. It's not like a plus symbol type cross. It's a crucifix shape, and it's lying on its left-hand side, down to the southeast, about halfway up from the horizon. Now, don't confuse it with the thing called the False Cross, which is a similar-looking group of stars in a cruciform shape, and which at the moment is higher up and also lying on its left-hand side. A lot of people do get these two star groups mixed up. The easy way to tell them apart is that the Southern Cross is smaller. Most people actually, they go out and they look for the Southern Cross, and if they've got a fair idea of what shape it is, they see the False Cross first because it's bigger. And they think, oh, that's the Southern Cross. But down below it is the real Southern Cross, and it's much smaller. Its stars are brighter, but the constellation itself is smaller. So that's people tend to not see it sometimes. It's a bit strange. Anyway, don't get confused. If you're going out to look for the Southern Cross, just bear in mind that there's another group of stars up there that looks the same shape, but it's a bit bigger. Now, just near to the Southern Cross are the two bright stars known as the pointers. These are Alpha and Beta Centauri. Alpha Centauri is the star system that's nearest to our solar system, and it's comprised of three stars. One of them, a small star called Proxima Centauri, is the actual closest of the three, but it's far too dim to be seen unless you have a quite big telescope and know exactly where you're looking. The Alpha and Beta themselves are really nice and bright, and Alpha, as I said, is a three-star system. The closest star, the tiny star, is far too dim to be seen, and even the other two stars that make up the system, they look like it's just one star to the naked eye. There are lots of double stars up there, and binary stars, and even triple star systems and more in the night sky, but to look at them just with the unaided eye, you wouldn't know. You need to get telescopes onto them, and you can then start to separate the two stars or three stars apart. So when you're looking at Alpha, you're looking at two main stars, which you can see separated. If you get even a small telescope, you'll see them separated. But the third one, Proxima, you won't see unless you get a really, really big telescope onto it and you know exactly where you're looking. Now, the Magellanic Cloud galaxies can also be seen pretty much due south this month. These are two small galaxies that are companion galaxies to our own Milky Way. To the naked eye, they look like just fuzzy clouds. hence the name. But you do need dark skies to see them, though. Where I am in a big city, I struggle to see the Magellanic Clouds because we've got so much light pollution around me. But if you can get somewhere dark, you don't have to be out in the country, just far enough away from street lights, a sporting field that doesn't have its lights on at night or something like that, or a park, or just anywhere we can get away from some lights, or just block the lights from view behind a building or something. And you do need to let your eyes adapt to the dark too. This is a thing that people don't often realise when they're starting out, is that you're going outside from being inside in a nice brightly lit house. You do need at least 20 minutes, 30 minutes preferably, to let your eyes get adjusted to the dark, and again, keep away from street lights and things, because that's just going to ruin it again. So really try and protect your night vision.
And don't use a flashlight unless it's got a red filter on it.
Yeah, red filter is a good thing to do. You can get some red cellophane's not the best thing to use, but if that's all you've got, that's fine. You can get special red filters to put over flashlights or torches. There are certain wavelengths that are better than others. And in fact, people have tested all sorts of colours to see whether they're better than red even, but red's a good bet to use. Yeah, so if you do need to go out and find your way around in the dark, yes, use a torch or a flashlight that's got a red filter on it. Now, the Milky Way, which is our galaxy, it's just our galaxy seen from the inside, basically. It can be seen stretching from the southeast to the northwest. And as you go north along the Milky Way, heading away from the Southern Cross, you go through some really good constellations, some of which most people would never have heard of. Ones such as Vela and Puppis, Canis Major, Orion. Orion's one that people might have heard of. Canis Major, you've got the star Sirius. It's the brightest star in that constellation. And it is actually the brightest star in the night sky as seen from Earth. So you really can't miss Sirius. It's nice and bright. Orion, the constellation of the Hunter, it's dominated at each end by bright stars. At one end you've got Rigel, on the other end you've got Betelgeuse, or Betelgeuse, as it probably should be pronounced. And through its middle, perpendicular, runs a belt of 3 stars. It's actually the Hunter's belt from which dangles his sword. So these 3 stars in a straight row are very easy to see. And also within Orion, you've got the famous Orion Nebula. Now, through a telescope, the Orion Nebula looks really, really good. But to the naked eye, it's just a fuzzy patch. And again, you need dark area and eyes that have adapted to the dark. But it's really good, even if you don't have access to a telescope. If you look up a picture of the Orion Nebula on the internet or something and see what it looks like, and then you go outside at night and, okay, all you're seeing is a little fuzzy little patch. But when you think, wow, I'm actually seeing that, and that's what that fantastic picture is that I saw on my screen, and I can actually see it, even if it's just a fuzzy patch, I can actually see it with my own eyes. And it's 1,500 light years away, roughly. And it's just the most amazing. It's really amazing when you see something in a book or a magazine or on the internet and you think, I wonder if I can see that. You can go out and you can. It won't look as good, of course, but you know that you are actually seeing something that's hundreds or thousands or tens of thousands of light years away. That's part of the fun of doing stargazing. Now, what else have we got? Low down on the western horizon, sort of after sunset, you've got a wedge of stars with a reddish-coloured star at one corner. This is the head of the constellation Taurus, and that reddish star is called Aldebaran. The eastern half of the sky in the evening during March is pretty bare, really. But later in the night, after the Earth has turned a bit on its axis and some more stars have come up in the east, we've got the constellation Virgo. Now, Virgo is a very big constellation. It covers a lot of the sky, and it, too, to the naked eye, looks a bit bare. But amateur astronomers just absolutely love it, because within Virgo is a huge cluster of galaxies, all sorts of galaxies spread over the constellation. Big ones, small ones, ones that are edge on, ones that are face on, different kinds, and backyard telescopes can reveal dozens and dozens and dozens of these. So amateur astronomers really love this time of year, getting on towards wintertime in the southern hemisphere and summertime in the northern hemisphere, because Virgo's up and therefore you've got lots of galaxies. Now, turning to the planets, what have we got? We've got Jupiter. Jupiter's big and bright in the northwest after sunset. You really can't miss it. It's about a third of the way up from the horizon. If you are struggling to work out which one of those things up there is Jupiter, so it's big and bright, but go out on the 14th and look for the moon, because the nearest bright thing to the moon will be the planet Jupiter. To see Mars, you have to be up before dawn, I'm afraid, so you've got to be an early riser or getting to bed late. Look to the east after about 5 a.m. and see if you can spot it. It looks like a medium brightness, reddish, orangey coloured star, although it's not a star, of course, it's planet Mars. But that's what it looks like. It just looks like a little orangey red dot. But that's that planet Mars, with all those rovers and things roving around it, and that helicopter that used to be flying around. I think it's done its dash now, hasn't it? The helicopter, it broke one of its or damaged one of its rotors. Yeah. But what an amazing thing though! It just lasted for so long, which most of these things do on Mars. They tend to last a long, long time. So that's Mars. Now, about half an hour after Mars rises, same part of the sky, Venus will rise above the eastern horizon. And look, you cannot miss Venus. You cannot mistake it for anything else because it's the biggest, brightest thing in the night sky other than the sun and the moon. So you'll see this whopping, huge, bright-looking star, in inverted commas, but it's actually the planet Venus. And about half an hour after Venus rises, there's another planet, which will be Saturn. Saturn will be rising over the eastern horizon, although in the first half of the month it'll be in the sort of beginning of the dawn light, so it'll be a bit hard to see. Wait until the second half of the month, and in particular, go out and take a look on the 22nd. Really, if you've got good weather, get up early before dawn, go out on the 22nd, because you'll see that Venus and Saturn have moved very, very close to each other. They'll only be about a third of a degree apart. That's really quite close. Now, of course, they're not actually really close to each other out in space. It's just a line of sight effect from our point of view on Earth. They appear to be in the same direction. And having them that close together, only about a third of a degree apart, is pretty great. And they're both quite bright. Venus is very bright. Saturn probably half that bright. But these sort of things happen several times during the year with different planets. But, it's worth getting out to have a look at any particular one if you get the chance, because the next one might be clouded out or whatever, or you might sleep in or forget to wake up or whatever. So 22nd of March, go out, look in the eastern part of the sky before dawn, and you should see big bright Venus, and right next door, fairly bright Saturn. And that, Stuart, is the sky for March.
That's Jonathan Nally from Sky and Telescope magazine. And this is Space Time. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more Space Time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.